All right, okay. Hello, everyone. Welcome back to Comp 3430 Operating Systems. I hope oh my gosh, I hope you're all doing okay today. It's been so hot this weekend, and today is, I don't know, it's just something else. Yeah, I did ride my bike today. I did indeed ride my bike today. I actually wore a mask to ride my bike today, which helps a lot. Even just like an old cloth mask is enough to keep the smoke smell out. But yeah, gosh, it was something else. On Thursday last week, after class was over, I had a mild panic attack because I got up to my office and people were coming to office hours and like things were going okay. And then as I'm kind of getting prepared to leave, I realized that I didn't have my microphones. So like the ones that I use to teach class with. And these were not exactly cheap microphones to buy. And so I was also in this time crunch of like, I have to get out of here because I need to, this is stupid. I need to meet my dad because my dad has a truck and my dad was going to help me go to Home Depot and get this picnic table. And so I had to meet him at a specific time. And like, I'm in my office, like rifling through my bag, trying to find these microphones. And then I come down to the classroom after that, and there's somebody else not teaching a class. There's like an engineering tutorial or something in here after that. And like I rudely barged into the room and I'm like looking here and trying to find it and I can't find anything. So I left on Thursday just like kind of in a panic, biking home, and I met my dad and we got the picnic table and it was all fine. And then I came back here at like 7 o'clock at night. And my little bag that has the microphones in it, it was just like on the floor, stuck here. So I was really happy to find it. And that made my weekend feel a lot better. And after Friday, I hope that all of your weekends felt a lot better than they were before that. I know that you had software engineering stuff due last week. You had stuff in my class due last week. I don't know what you have in software engineering this week, but you got nothing due in my class this week, so good, yes. This is gonna be a little bit more of a relaxed pace, I guess, this week. But yeah, welcome back to operating systems. So what I want you to do by the end of today's lecture, I actually have two things that I want you to be able to do, but I've only written one here. The first one is about deadlock. I want to finish up the deadlock example. Specifically, I want to go through the process of applying total ordering of lock acquisition to this example that we were looking at. So the strategy that I described in class last week was that I want us to be able to basically take these accounts and sort them. So they're always going to be in an order. And that means that we're always going to acquire one of the accounts locks before the other one. And we'll never get into that situation of circular wait. So the example, the physical example that we were doing in class last week was with the pen and the tablet here, where if we can make it so that we're always going to acquire the pen before we acquire the tablet, no matter who it is that's trying to do it, if I always get the pen first and I wait for the pen if it's not available, I can never get into this situation where I've got two or more people that are waiting for different parts while the other one is holding these other parts. So physically, always acquire the pen first, and the strategy that we're going to apply with this deadlock example code is I always want to acquire the lock in the account that has the lower address. So like in memory, we're going to say that these accounts have addresses. You probably want to modify this so that these accounts have identifiers, unique identifiers, and then sort them based on that in practice. But for us, for today, we'll take a look at using memory addresses to do this, because we can assume that the memory addresses themselves are unique. But the other thing I want you to be able to do by the end of today's lecture is begin to use condition variables in a program. So locks in multi-threaded code are pretty cool because they will allow us to do mutual exclusion. I can make it so that when I have a critical section, I can guarantee that only one thread of execution will enter this at a time. But the problem with locks is that they enter it immediately when it's available. And there are circumstances where I might want to cause a thread of execution to wait for there to be data available, rather than constantly entering a critical section to check to see if there's something there. This is actually a pattern that we used with signals, and I'm going to use the word signals today to describe this idea of condition variables. The idea is the same, but we're talking about this now in the context of a multi-threaded process as opposed to multi-process programs communicating through each other with signals. I want to do a really basic mechanical, like this is how a condition variable is used in a program. And then what I want to do is I want to build a more complete example of a realistic place where condition variables could be used. So with the data structure and solving a problem that's an actual problem that is actually done in actual computing and stuff. So first things first, let's take a quick reminder of what these 4 conditions for deadlock are. We've got this new kind of concurrency bug that is called deadlock. And the outcome of this is ultimately that we have threads of execution that are running, 2 or more threads of execution that are running. And the observation that we're able to make about this code is that it just gets stuck. There's no progress being made. They might be using 100% CPU, but they're not actually doing anything. They just get stuck and then no further progress gets made. Deadlock is a condition that can happen when all 4 of these conditions hold. And like I said last week, when I say the word hold, I mean they apply in this case. So we can show that this is actually true for the piece of code that we're looking at here. The 4 conditions are mutual exclusion, hold and wait, no preemption, and circular wait. And I want to start today's class by doing a little quiz. So I'll hold this QR code up for about 10 seconds, and then I will switch over to my Mentimeter. Okay, I'm going to switch over to the Mentimeter now. And I'll hold this open for a couple more seconds. The code is at the top in case you are still joining up. All right, so these are questions about concurrency. These are questions about locks and lock implementations. And then these are questions about deadlock. So list insertion.c was one of the concurrent code examples that we were looking at. Okay, so awesome, yes. Maximizing concurrency in theory here is where we're going to take our node structure that we've got for this list, and then before we make changes to this node, so we're changing the next of this node, we're going to lock it. That means that we're going to be able to have insertions that don't deal with the same node happening literally at the same time. So I can insert after head and I can insert after node 50,000 literally at the same time because they're different nodes that we're inserting after and they don't really affect each other. Function scope here, just to be clear, what I mean by function scope is that this is being declared as a stack allocated lock, and that would ultimately mean that every thread gets its own lock. And so I'm spiritually going to give credit to this answer because it 100% maximizes concurrency because every thread will always be allowed to execute concurrently. If everybody gets their own lock to hold, there are an infinite number of pens here. Everybody gets to go concurrently. And we really don't actually want that because it's going to result in not what we're hoping for. But I want to give some spiritual credit for that. File scope here, this actually minimizes concurrency. So if I have file scope, this means that anytime I want to insert into any list, everybody else is going to have to wait. It doesn't matter what list I'm inserting to it. It doesn't matter where I'm inserting to it. If I'm making this insertion happen concurrently, we're just going to have all these different insertion operations sitting behind each other waiting. List scope is a reasonable choice for in a place to put the lock, similar to node scope here. But the difference between node and list scope is that with lists, now we're going to make sure that no threads are able to execute insertions concurrently to one list. But between different lists, we're going to be able to insert things concurrently. All right, awesome. Okay, so here's our next question. And this is about a type of lock that's described in our textbook. Okay, yes, so awesome. I don't know. I really like the idea of a ticket lock. I think this is a really elegant solution to implementing a lock, because we're implementing this lock structure and not describing any kind of data structure at all. We're literally just got this counter and we're giving out numbers, but it's implementing a queue. We're actually implementing a queue of these tasks. So in the case of a Linux system, we're internally implementing a queue of these struct task struct in our own code by giving out these tickets and causing these other threads of execution to wait while it's not their turn. I really like this, and I think it's a really elegant implementation of locks and a really cool way to have a data structure or an abstract data type built into something without actually encoding that anywhere. I think that's really cool. Has anybody actually been to the Space Needle before? I'm looking at this and I'm realizing I've never looked at these tickets. Yeah? Have you been to the CN Tower too? Okay. I wonder how similar they are to each other. That's a question for a different time, I guess. Okay, that's the only reason you remember why you went there? Okay, because you were too young to otherwise remember it? Okay, okay. All right, so this question now is about processes. Okay, we're all over the place here, but the big one that we picked here is the one that I've got in my mind. Reading and writing ends of the pipes is like acquiring locks. I'm actually gonna kind of specify further that it's more like using condition variables, but we haven't really talked about condition variables yet. It's more like using condition variables, but condition variables themselves are acquiring locks, using locks to be able to cause threads of execution to be able to enter a critical section. And it's possible for us to make a connection between processes and pipes and ends of pipes in terms of reading and writing these ends of pipes. So read blocks. And if read is blocking because there's possibly somebody else somewhere in some part of my code that's going to be able to write at some point, even if it's me, then I'm going to be stuck in this situation where I'm not going to be able to proceed past this point. Yeah. So the question is that write is something, I'm going to try to repeat, I'm going to do my best to repeat this, yeah. Could this also be because write can also block if the buffer for writing into gets full? Is that the end of the question, or was there more after that? Okay, so yes, if there's nobody reading the end of the pipe, then write is also going to get blocked. The difference is a semantic difference, I guess. With reading, you're suspending yourself if there's nobody available to, there's no data available in the pipe to be read. Whereas the reason why you're getting blocked with write is there's too much data in the pipe already, but the effect is the same here. Yeah. Fork and wait is like acquiring locks. I want to give some spiritual credit to the wait specific part of this. Wait is definitely like waiting around for something to return or something to finish. So there's some idea of it's possible for my code to get into the state if my child process is also stuck for some reason. It's spinning infinitely and it's not going to proceed past a point. It's possible for us to say that wait itself is going to lead to this deadlock situation. But in my mind, processes and pipes here specifically is about reading and writing into the pipes, and that's kind of like acquiring locks. Bike enjoyer. All right, Leroy. Okay, so these now are all questions about deadlock. Okay, good. Good. I am so delighted that we're both picking just the answers that I'm thinking about here. So I'm going to say that mutual exclusion means both of these things. And I'm going to say that it effectively means both of these things equally to me. The other option here, exactly one thread being allowed to enter a critical section at a time, I'm going to say here that the critical section in this case is the resource. This is a weird way to think about it, but I'm being allowed and permitted to enter this critical section, and nobody else is being allowed to enter this critical section while I am in it, and that effectively means that I'm holding this resource that is the critical section. This is enforced by literally holding a resource, like a lock. I want to be able to hold a lock, and that causes other threads of execution to get stuck waiting for me to kind of abstractly define this idea of a critical section here as a resource itself. Here's our next question. You might sense there's a pattern to these. Okay, good. Yes, excellent. No preemption here is not being able to forcibly remove resources from a thread once it's been held. I want to ask this question partly because these two options here, so threads never having the CPU taken away by the OS or disabling hardware interrupts, the hardware interrupt timer. I want to point these out because of the idea that preemption here is an overloaded term. It's overloaded in the sense that it means two different things in two different contexts. Preemption is definitely the description of, I'm going to take the CPU away from you right now so that the OS can take over again. The hardware timer will interrupt and preempt the task that's on the CPU right now so that the OS can take over and schedule a different task. That is absolutely something that's happening with preemption. But in the context of threads, this also means that we're not going to be able to remove the resources that are held by that thread of execution. So I've got this lock. You're not able to take the lock away from me. It means more that than the CPU. Threads that hold a lock are preemptible. I can take that thread off of the CPU and it will be taken off the CPU and some other task may get to go, but I'm not from the thread. ROS doesn't really know anything about locks in this case. It's just memory that this thread is using. So while I can take the thread, I can preempt this thread, I can take it off of the CPU. In the context of threads, what I'm really thinking about here is I can't take the lock away from the thread once it holds it. I can't forcibly take it away. the thread is able to give up the lock if it wants to, but it cannot have it taken away by somebody else. Is that okay with everybody? Awesome. Okay. Here's our next question. Okay, yeah, awesome. So holding a resource while waiting for another resource. Once I've acquired a lock, I've succeeded in acquiring a lock, or I've succeeded in acquiring some resource, and I want to acquire another one. I'm going to wait for that other one to be given to me or being given up by somebody else. And while I'm waiting for that other resource, I'm just going to hold on to the one that I got. So with our physical tablet here, we're in the situation where once I have the pen and I'm waiting for the tablet, I'm going to hold on to the pen while I'm waiting for the tablet. I don't want to give this up, because if I give this up, then it means I have to maybe wait longer than I was otherwise going to have to wait here. The other two options that are picked here, so holding a lock while waiting for the CPU and holding the CPU while waiting for a lock or resource. Holding the CPU, I'm going to say, is just kind of like running the task on the processor. Holding a lock while waiting for the CPU, this is kind of reasonable, I guess, but the idea then is that eventually we're going to get the CPU back and then we'll be allowed to proceed. The best answer here is going to be, I've got one resource, I'm waiting for the other resource, and while I'm waiting for that other resource, I'm going to hold on to the lock that I've got or the resource that I've got. Here's our last of the 4 conditions for deadlock. Okay, awesome. The specific example that we've been looking at is for 2 threads. We've got thread 1 that's depositing from account 1 to account 2, and thread 2 that's doing deposit from account 2 to account 1. But generally, there's n threads and there's n resources, and they're all just in a circle waiting for each other to give up the other thing that we've got. So we're doing a very specialized example with 2 threads, and so it's very reasonable to pick this one, but very generally it's n threads waiting for n resources. Where we're in this state where everybody's got something and we're all waiting for somebody else to give this thing up. Here is our very last question after this leaderboard. Did Leroy hold on here? Oh, Ashley took over. Okay. We got 1 question left, so this might be a big shakeup. Here is our last question about deadlock. I'm really secretly rooting for Bike Enjoyer here, but okay. All right. What can we say about code if all 4 of these conditions hold? And the answer is both. Maybe it will deadlock, and also maybe it won't deadlock. I mean, these say the same thing ultimately, but maybe it won't and maybe it will. If they all hold, we can't guarantee that this code is going to deadlock. And the guarantee was demonstrated by me trying to run deadlock.c over and over and over again, and me never being able to do it, but somebody else in class being able to do it like 2 out of the 8 times that they were running it. I was able to run it with Hyperfine very quickly, and then I was able to see that it was deadlocking because Hyperfine just kept having its ETA go up and up and up and up and up and up forever. But the best we can say about it is that maybe it will deadlock and maybe it won't deadlock. If we are able to break any of these conditions, I break mutual exclusion. I take locks away. Deadlock can never happen. We might segfault, but deadlock will never ever happen. I break circular wait, I do total ordering, which is what we're going to do in a moment, deadlock cannot happen. I can guarantee that deadlock will not happen. That's the only kind of guarantee that I can make about deadlocking code, is that deadlock will not happen, provided that I can show that one of these 4 conditions for deadlock does not hold. I've broken one of those 4 conditions. All right. Whoa. That was tight. So congratulations, Ashley. Congratulations, Puffy and Leroy, and my secret favorite bike enjoyer here. Thank you all for participating in that. Does anybody have any questions about these before we take a look at the deadlock code? We're good? Okay, awesome. All right. So I would like to update deadlock.c to break the deadlock. There are a few options that we could apply to this. Put the lock in the transfer object is something that doesn't work. And the reason that putting the lock in that transfer object that we have in deadlock.c doesn't work is that effectively putting the lock in the transfer object causes it to be a thread local lock. Everybody gets their own lock. There's an infinite number of pins. Everybody just gets it immediately and they're allowed to proceed. So putting that lock there will still put us into a state where deadlock can possibly happen, because we might have that back and forth situation. Having a file scope lock will definitely break 2 of the conditions, but it will then serialize or put into sequential order all transfers between any account, whether they're related or not. So account 1 and account 2 and account 3 and account 4, they're completely separate accounts, but we're still going to have to wait to transfer between account 3 and account 4 until after account 1 and account 2 have finished. We have definitely broken hold and wait, and we've definitely broken circular wait, though more hold and wait than circular wait. Because we've effectively locked lock acquisition, you can't even begin to acquire one of these 2 other locks until you've acquired the first one. But the problem is that we don't have concurrency anymore. We're going to do sorting accounts here. The one that we're going to focus on is sorting accounts. And this is good. It's going to work. It's a little bit more complicated. There are more lines of code that we have to add for this. We have to do things like changing the direction of the amount, so changing the sign of the amount based on the order that we put the accounts into. With more lines of code, there are more chances for us to screw this up. So it's kind of complicated. It's not crazy complicated, but it is a little bit more complicated than the other approaches. The other option here is to use pthread mutex trylock. Pthread mutex trylock, and I'm going to bring up deadlock.c here so I can specifically point at this. So this is in our thread management repository, and this is up on the course webpage. There's a link to this on the course webpage for today. Adding pthread mutex trylock, the place where I would put that is right here. So rather than just do the lock, this function right here will block if I'm not allowed to get the lock. Trylock will not block. Trylock will immediately return. And the immediate return will tell me one of 2 things. You got the lock. Great. Nobody else is going to enter this critical section because you have the lock. Or alternatively, it will return and say, the lock is held. There are 2 paths here. One is, I got the lock, so I'm just going to proceed with doing the transfer. I'm going to do my critical section here because I know that I have the lock. The other path is, somebody else holds the lock. And if somebody else holds the lock, then what I'm going to do is give up the other lock that I hold right now, so that if somebody else is waiting for that lock, then they'll be able to acquire it. And then I'll try again. And then I'll try again, and then I'll try again, and then I'll try again in a loop structure. Once I get that lock, then I will try to get the next lock, and we'll go through the same cycle again. This works. It breaks hold and wait. It will stop us from being in this situation where I'm blocking here, waiting for the other thread of execution to release this other lock. But the problem now is that we could still get into a situation where we've got two threads competing for opposite locks. They're both doing try lock and then giving up, and then doing try lock and then giving up, and then doing try lock and giving up. And they get stuck in this kind of a cycle. This will probably eventually end. Eventually, one of these threads is going to get scheduled in such a way that it will be allowed to get both locks and then finish. But they might be spinning here for a little while they're waiting for each other. The one that I really want to do here is to begin to apply total ordering of lock acquisition here. So I've already written this comment here on lines 43 and 44, and so I want to encode what I mean by this operation. So I'm going to start by, instead of using the from and to properties of this deposit thread args structure, I'm going to make my own two pointers here, from and to. I'm not going to initialize them yet because I'm going to initialize them in this conditional statement that I'm going to use to put them into a specific order here. The question that I'm going to ask is if args from is less than args to. And so I'm using addresses. I'm using addresses as a unique and comparable identifier for these two different accounts. They're different accounts if they have different addresses, so I'm just going to compare the addresses to see which one of these addresses is less than the other one. In practice, I probably want to have an ID field in the account object itself. I want to put an integer in here so that I can actually just do sorting on the identifier of the account itself. What I'm going to say here is that if from is less than 2, then I'm going to say that the from that I've allocated here is equal to args from. The to that I've allocated here is equal to args to. And I'm also going to declare an amount. And I'm going to say that the amount is equal to args amount. So if the from account is less than the to accounts, then I just want to proceed with this in the same order that it's in right now. I don't want to change anything. In the opposite case, else, I want to say that from is equal to args to. I want to reverse the order of these accounts, and I want to make it so that the account that's less than the other one will be from, will always be from. And that means that I'm always going to try to acquire the lock of the account that is the least amount first. I'm going to do ordering of these accounts so that I always get the lock in the same order. I'm going to say 2 is equal to args from. So our goal here is reverse the accounts so that we always acquire the lock of the account that is smaller than the other one. The account that has the ID or the address that is less than the other one will always be from. It's always going to be from in this case now. If I'm reversing the order of these accounts, then I want to say that the amount is equal to -1 times the amount that's in args here. I need to reverse the amount of the transfer. If I'm changing the order of these things, if I'm taking the to account and making it the from account, I want to negate the money that I'm sending between these two accounts. There's already a bug in this code, which is why I'm saying that this is more complicated. The bug is, what if they're equal to each other? What if it's just transferring money from an account to itself? I'm not convinced that this works, and I don't want to dwell on it very long, but I'm not convinced that this works if this is the same thing. Now, what I want to do is, I don't want to use args from anymore. I just want to use from. So whatever I've assigned to be the from account is the one that I want to use. I don't want to use args from. I don't want to use args amount. I want to take all of these args things away and just use the function or stack allocated or thread local versions of the account names that I've got here. So in this case, what we're going to have is total ordering of our locks. The account that has the smallest ID will always be attempted to be locked first. So I'm going to go down to my main function right now really quickly and recall that the whole reason that we were in this situation are these two blocks right here. The transfers that I'm making are take money from account 2 and put it into account 1, take money from account 1 and put it into account 2, so kind of back and forth. In the first case here, our from is going to stay as account 1, and our to is going to stay as account 2. In the second case, the second line that we've got here, inside of our function, we're going to reverse the order of these. So I'm going to make it so that account 1 is from and account 2 is to, and I'm transferring negative 100 between the two of them. So I'm going to add to account 2, and I'm going to remove from account 2, and I'm going to add to account 1 here. So I'm doing total ordering of our locks by reordering the accounts and the locks that we're working with up here. We okay with that? Yeah. Negative balance in the opposite direction. Here. Yeah. Yes. Yeah. Again, complexity, just additional complexity with doing this sorting. This code is buggy, but it won't deadlock anymore. That's the benefit that we have here. It's buggy in different ways. Any other questions? Yeah.
This solves hold and wait, right?
This breaks circular wait. Yes. This breaks circular wait because we're never going to have somebody holding account 2's lock before getting account 1's lock. We're always going to try to acquire account 1 first. So that means here, where previously we had this statement here, T1 gets account 1 lock and T2 gets account 2 lock. This is going to be T1 gets account 1 lock. T2 waits for account 1 lock. It's going to get stuck before it's even allowed to get past the point of getting the from lock. Yeah, so this now is, this is with or without ordering, and this is with ordering here. Okay, awesome. All right. So with that, what I am going to do is we're going to come back here and we're going to switch gears. As you probably saw in your inbox today, I sent you back your test results, so you have some feedback there. If you have any questions about your assessment, whether it's questions about the feedback that you got or uncertainty about the grading guide compared to what you wrote, I'm going to politely request that you email me about that as opposed to coming to talk to me in my office at first. I like to read what you have written down on the paper. And I don't know about you, but I find it very awkward for somebody to be watching me while I'm doing that. So I just prefer to get the email first, but I'm ultimately happy to talk about it. But I do want to make sure that you get a fair assessment on your test. So please let me know. But I did want to show you some pictures of my cat. So this is Walter. This is from the weekend. This is actually the picnic table that I was talking about earlier. This is Walter on a hot sunny day. And this is Walter in puddle mode, where he kind of just flops on his side and his saggy belly is, you can see, just kind of like sprawling out there a little bit. I wanted to share with you some of my favorite pictures from your tests, because I think that some of you did a great job. Some of you, and I say this very lovingly, are terrible at art, but I say this as a person who is also very bad at art. I liked this one because it almost looks like the corruption of the image has made Walter angrier. Like he was quite angry here, and it somehow made him angrier on the second one. I liked this one just because it like takes everything that you know about me. There's a bike there, and I've got a cat. That's the two things that you know about me. Okay, so that's the main things here. And I guess that I have a nice floor, but I like that the picture is there. And I can't actually quite read what this says. Beautiful something, beautiful stained glass painting. And then it's corrupted by the Dear Diary here. I love this one because it was very much a puddle situation. This one was also really nice, although I was happy to see, I guess, that the teeth went away with the corruption of the image. This one was nice, and it says there's a better drawing in the back page, and this is what was on the back page. So I'm really happy that this person did that, and I'm flattered. It was a very nice picture that they drew of me. I like this one because you can start to see this little saggy belly that Walter has here, and that Walter is slowly disappearing from this corruption. This one was just, I don't know, some of you are terrible at drawing. Yeah. And again, I'm saying this very lovingly, like I'm not criticizing your art skills. You've seen what I can draw, so just, yeah. Again with the puddle, but I just love this one. It's minimal and it's great. This one was, I warned you in the previous answer that this would happen, and then it happens. And also Walter has this nice little saggy belly. This one is great. The picture of the cat is really nicely done here. I really liked this one. The corruption was just so like, I don't know, it was well done. I really, really liked this one. The saggy belly gets much bigger in this one. This one was also just nice. There's a nice sunshine. And then this was the last one I've got. I have no idea what's going on here. I love that Walter is standing up on legs like this. Kind of looks like a penguin almost, but with cat ears instead of cat body. So thank you all for sharing that. You know, secretly, this is like my little treat after doing grading, is I get to look at all these pictures, and it brings a smile to my face. So thank you for that. But now let's actually talk about operating system stuff. So locks are what we've been focusing on in terms of synchronization with threads, synchronization with granular concurrency here. Locks prevent concurrent access. So we've got these critical sections, we've got these race conditions, we put locks around the critical section, acquire the lock, release the lock. And the goal here is that I want to make sure that many threads of execution are not allowed to run the same block of code that we've got here. Only one will be allowed in at a time. And this is great, but there are circumstances where I don't want the other half of what happens with this, which is that as soon as the lock is available, I'm allowed to enter the critical section immediately. So if the lock is available when I get there, I will just immediately enter the critical section. If the lock is not available when I get there, I will immediately enter it when it becomes available. I'm not going to wait around. I'm just going to get into the critical section and start doing stuff. And there are circumstances where I don't want that to happen. A condition variable is pretty closely related to a lock structure, but it has an additional option which effectively says, don't enter the critical section until you are signaled to enter the critical section. So we're going to use a lock with a condition variable, but we'll have this additional semantic idea of, I'm going to block even if the lock is available, and I'm going to wait here until somebody tells me that I should start entering this critical section. So I want to take a look at this in two different ways. The first is that I want to look at a very contrived example. This is just mechanical usage of condition variables. There's no meaningful purpose to this code. It's just going to be, this is how condition variables work. This is how I write the code to use a condition variable. This is what the semantics of using condition variables mean, but it will not actually do anything that's meaningful. We're going to launch a bunch of threads. They're going to wait until the main thread of execution signals them to do something. They will do that thing. They will all exit, and then the main thread of execution will exit. There's no purpose to this code other than mechanical usage of condition variables. The other thing that I want to do is spend some time writing some realistic code that uses condition variables. This is not good code from the perspective of I encourage you all to use this in your projects later. This is more of this is a way that you could use condition variables in something that isn't contrived. This is going to be an actual real purposeful example of using condition variables. So what I want to do is write some code here. I encourage you to follow along with me if you want. This code that we've got is in this repository that is again linked to in today's lecture notes. If you've got this repository, you should pull it because I pushed some more things that are going to get us started with today's stuff. So I'm going to pop over to my terminal here. I'm going to quit out of deadlock.c, and in this repository, I'm going to do git pull. And there's a bunch of extra stuff that I've got in here. The two new big things that we've got are conditionvariables.c. So this is the file that we're going to work with to start. And then the other one is a directory that's full of stuff. The directory that's full of stuff here is called 3430 pool. And we'll talk about that when we get to it. So the main thing that I want to focus on right now is conditionvariables.c. So I'm going to open this up. And I want to take you through some of what's here already. The very first thing that I've got here is a function that's called getTID. We have seen and used getPID and getParentPID. These are the two system calls that we've been using to get what our process ID is for our process and to get the parent's process ID. On Linux, this is not portable code. This is something that's only going to work on Linux. On Linux, there's also a system call that you can make that's called getTID, which is to get the threads identifier. There is no libc version of this. So when we're calling getPID, we're calling a libc function, which does what we've got here. This is the way that we would invoke a system call directly. There's a function here that's called syscall, and what we pass to that is going to be the number of the system call that we want to invoke. So sys_getTID, I don't know what number it actually is, but there's a number under here that represents the system call number. This is Chromium OS. All right, so every system call here has a number on the different architectures that we've got. So these are all the system calls, and many of these are system calls that we've used. System call for read is number 0. System call for write is number 1. Open is number 2. Close is number 3. The getTID is 186. I don't know. I don't actually know what number this is. It's not really that important to me. The other thing that this table is showing us is kind of interesting stuff, which is the syscall function also takes additional arguments that you can pass to it, and it will set up the context switch and the mode switch so that it will take all these and put them in the correct registers and stuff. For getTID, it doesn't actually take any arguments. It just returns the thread's ID for us. So here we are manually invoking, and I'll put this in quotes, we are manually invoking a system call. We're asking the OS for the currently running threads identifier here. We've got two additional things up at the top here. We've got a mutex, we've got a lock. This is something that we have used before. The other thing is a condition variable itself. We've also got a counter here, and the counter here has a different type than we have used in the past. The type that's here is an atomic uint. So this is an unsigned integer, but it's marked as atomic. And what that means is that as an atomic integer, operations that are not a single operation are going to be atomic. So plus plus on a type of this will be an atomic operation. For any kind of operation that we could do to this thing. The function that we're going to pass to pthread create is called work here. It takes one argument, which is args. We're not going to do anything with that args argument. We're printing out that we started. We're printing out that we finished. The main function is creating all these threads. It's waiting for them to finish. This isn't exciting code right now because if I were to compile and run this, which I'm going to do right now, this is lecture 16. It just finishes immediately. It just prints out all the thread IDs and then finishes immediately. The thing that I really want to be able to do, though, is I want my main thread of execution to be able to launch all these threads, and then I want all the threads to wait for my main thread of execution to tell them to start. I don't want them to do anything until that happens. So I'm going to start working in my main thread of execution here. In my main thread of execution, the very first thing that I want to do is I want to initialize my condition variable. I've declared it as a file scope lock, as a file scope variable, sorry, alongside the file scope lock. So it's sitting up there at the top. It's outside of any function, and that means that all threads of execution are going to have access to this variable. I want to initialize my condition variable here, and the way that I'm going to do that is using pthread const init. Pthread const init takes two arguments. One is the condition variable itself that I want to initialize, and then some other attributes. We're not going to be applying any additional attributes to this right now, but I welcome you to look at the manual page to see what other kinds of things you can do to a condition variable. We're just going to pass null to this because we're not going to initialize this with any other kind of attributes. So I'm going to say pthread const init. I'm going to pass the address of the condition variable itself. I'm going to go back up to the top because I've forgotten its name. It's just called CV. And null. I don't want to pass any special attributes to this thing. I want my main thread of execution to start all the threads. And all of the threads are going to tell the main thread of execution that individually they're ready. And so the variable that I've got up at the top is a counter. And each thread of execution is going to start, and it's going to increment that counter by 1 to say, I am ready, and I'm waiting for further instruction about what to do. While all of my threads are starting up, I want my main thread of execution to wait for all of these threads to start up. So I want to block until all threads have actually started. And so I'm going to do this by saying while num threads ready, sorry, is less than num threads. So each thread of execution is going to do ++ on this inside of its own function. While threads ready is less than num threads, I'm just going to spin. I just want to keep blocking here until this situation is done. So spin and do nothing until all threads are ready. Once all the threads are ready, then I want to have my main thread of execution block again, but this time I want it to block on input from me. So I'm going to say printf, all threads are ready. Press enter. To send signal. And I'm going to say get char here. I'm not going to use the return from this. I'm just going to block. I just want to wait until I press enter on my keyboard here. I'm using the word signal here because we're going to send a signal to our threads. Condition variables, when we're talking about condition variables, the verb that we're using here is signaling them. We're sending signals to our threads of execution that are currently waiting on the condition variable itself. This is not the same as kill. This is not the same as signal handlers. This is a different mechanism that's doing this, but we're using the same word to describe the idea of what we're trying to accomplish. So my main thread of execution here is going to block twice. It's going to block until all threads report themselves as ready, and then it's going to block until I hit enter on my keyboard. Once I hit enter on my keyboard, then what I want to do is I want to send a signal to all waiting threads I want to send a signal to all waiting threads that they should wake up. Anytime I work with a condition variable, I need to use the lock that's associated with this condition variable. So step one, I want to acquire the condition variable's lock. So my main thread of execution is going to say pthread mutex lock. And I want to pass to it the lock that I've got here, which is CV lock. Step two, send a signal. And the signal that we're going to send with this is using a function called pthread cond signal, which is the same manual page, Pthread cond signal says, I want one thread to wake up, just one. I want just one thread that's waiting to wake up. The other one is broadcast, and broadcast says everyone that's waiting should wake up. But for now, I'm just going to wake up one thread of execution. So I'm going to send a signal, either pthread cond signal or pthread cond broadcast. So I'm going to say pthread cond signal for now. And I want to send that on the condition variable itself. So I'm going to acquire the lock. The main thread of execution has the lock right now. I'm going to send the signal to a thread that's waiting. And then I'm going to finally unlock the lock. I want to release the lock after I have acquired it in the main thread of execution. After this, I'm still going to wait for everyone to finish. And then once everyone's finished, we will exit the main thread of execution. So now what I want to do is I want to make changes in the thread of execution itself. The thread of execution itself is operating in this work function. And the very first thing that I want to do is I want to signal to my main thread that this thread is ready. And the way that I'm going to do that is using that thread's ready variable here. So I'm going to say threads ready plus plus. Threads ready plus plus would be a race condition if we were not using that atomic type. Because we're using that atomic type, we can just do a blind plus plus, and we're not going to run into that situation that we had with that textbook sample where we had that plus plus in a loop and we were losing add operations. This is going to make sure that those three instructions are always going to be put into some order such that not multiple threads of execution are going to interfere with each other. So I want to signal to main that this thread is ready. Once I've signaled to main that this thread is ready, I want to cause this thread of execution to suspend itself until it has been signaled. I want to go to sleep until I have received a signal from someone else to wake up again. We can't do this with just locks. If we have just locks, we either immediately enter or suspend until we are able to enter, and then we will immediately enter that critical section. I need to use locks because this is a critical section still. I only want one thread to be able to get here at a time. But the difference is I want them to block until they have been signaled. We're going to use this condition variable, and the structure is going to be similar. Step 1, acquire the lock. So I'm going to say pthread mutex lock, and I'm going to pass to that CV lock. I want to acquire the lock. Then I want to wait on the condition. I'm going to call this function. pthread cond wait says, I would like to register myself to be notified when somebody sends a signal on this condition variable right here. Until that happens, I'm just going to go to sleep. I'm just going to wait. I'm going to block. I'm not going to do anything. So step 2, wait on the condition variable. I'm going to say pthread cond wait. I'm going to pass to it the condition variable that I'm waiting on. And the second argument here is the lock. The semantics here are a little bit weird. The semantics are wait on the condition variable, part A, release the lock, give up the lock. On line 39 here, I hold the lock right now. That means nobody else will be permitted to wait for the condition variable because this thread of execution currently holds the lock. So the first part of waiting on the condition variable is giving up the lock so that other threads are able to wait on the condition variable. Part B, go to sleep. Sleep, go to sleep, suspend, block. Release the lock, and then just put yourself to sleep. So you're not going to proceed past this line because you suspended yourself. You put yourself to sleep until somebody notifies you that this is happening. That means that pthread cond wait, kind of like pthread mutex lock, it blocks. We're not going to proceed past this line of code until an event has happened. Once I wake up, so I'm executing code past pthread cond wait. I hold the lock. This is kind of weird because I'm not explicitly trying to lock the lock again. The semantics of pthread cond wait are such that I acquire the lock, I have the lock. I'm going to put myself to sleep, and before I put myself to sleep, I'm going to release the lock. That's going to allow some other thread of execution to get the lock and then put itself to sleep. And then it will release the lock. And then some other thread of execution will get the lock, suspend itself, and release the lock to allow someone else to wait on this lock. We can get into a situation where many threads of execution have called pthread cond wait, and many threads of execution are suspended here waiting. Our main thread is going to send the signal. So we're waiting for all these threads to start up. We block, we press enter. The main thread of execution at this point will be able to acquire the lock because all 10 of the threads that we've got in this code example will have gone through this entire process of acquire the lock, wait, release the lock, acquire the lock, wait, release the lock, acquire the lock, wait, release the lock, acquire the lock, wait, release the lock. Nobody holds the lock at this point. Our main thread will get the lock. It will send a signal. I would like one thread of execution that's waiting on this condition variable to please wake up. For a thread of execution to be able to please wake up, it needs to be able to hold the lock. I will ask for one thread of execution to wake up by sending the signal, and then I will unlock the lock so that that thread can actually do something. Until the lock is available, it's still not going to be able to return from this pthread cond wait. Once I hold the lock, then I'm going to do something. So this is now in my critical section. I hold the lock in the critical section. I'm going to do some important work. I'm going to print out a message that says that I've received the signal. And then after that, I still need to release the lock. Once I unlock the lock, I'm going to finish my thread, and then I'll exit from my thread of execution here. So I'm going to quit my manual page. I'm going to make this. I'm going to make that a little bit smaller. And I want to step through this again, just really quickly. Concurrency breaks my brain. It really breaks my brain because starting to think about all these different things happening at the same time is just like, it messes with me a little bit. And so it helps me to be able to see this code and like step through what's happening for each of these things in the context of like the main thread and then maybe one additional thread of execution. So our main thread starts. At this point here, right up until we start this loop here, there's one thread of execution in this process. There's the main thread of execution. Our main thread of execution is going to create 10 threads in this case. All of these threads are going to work on something. They're getting this work function to be executing their code in, and we are passing something to them, but we're not using that in the function itself. Once the main thread of execution has called pthread create, then we're going to say that a thread of execution will be allowed to start. A thread of execution is going to do this printf. I've started working in this thread of execution. It's going to increment threads ready ++. It's going to acquire the lock. Nobody else holds the lock right now. The main thread of execution is still busy starting up other threads. This thread of execution will get the lock. It will suspend itself, and it will release the lock. So at the point of line 40, one thread of execution is stuck here waiting. Nobody holds the lock. This happens for all 10 of the threads that we've got. Our main thread of execution could spin here if not all of them has started up at this point. So it might block, but more than likely this is a conditional statement and it just steps through it immediately. it will get blocked here. All 10 threads are currently suspended. They're all waiting on this condition variable. When I press enter, my main thread of execution will continue. It will get the lock. It gets the lock because nobody holds the lock right now. All of these threads acquired the lock and then released the lock when they suspended themselves. The main thread of execution will get the lock. It will send the signal. And then for these threads to be able to wake up and enter their critical section, it must release the lock. It has to give up this lock. pthread signal says wake up exactly one thread. Allow only one thread to enter the critical section. One thread is going to wake up after this line has finished. After I've released the lock from the main thread of execution, one thread will return from pthread wait. It will hold the lock. It gets the lock as soon as it is returning from pthread wait. It holds the lock. It prints out this message. It releases the lock. It lets somebody else get control of the lock. It finishes itself, and our main thread here, whoops, oh, I'm getting all messed up. It finishes. Our main thread control takes over, and it's going to wait for everybody to finish. I'm going to make that. I'm going to zoom in on this one, and I'm going to run it. All 10 threads have started. All 10 threads have acquired the lock. They've waited on this condition variable. They've released the lock. All 10 threads are currently suspended. They're all waiting for me to send a signal to them. I'm going to hit enter on my keyboard, and the main thread of execution is going to send a signal to one of them. Only one will wake up. 586964 happened to be the first one to get there. It happened to be the one to wake up. It finished the thread. The main thread is now stuck waiting for all the other threads to finish. So I'm going to change this just one little bit. And I'm going to say here, instead of pthread signal, I'm going to say pthread broadcast. pthread broadcast says, wake up everybody that's waiting. Everybody that's currently waiting will get a turn to go. I'm going to hit Control-C down here. This is never going to finish. I'm going to make it. I'm going to zoom in here and run this again. All 10 threads have started. They've all, in turn, acquired the lock, waited on the condition variable, gave up the lock. They are suspended. The main thread is blocked, waiting for me to press enter right now. I'm going to press enter, and then all 10 threads are going to get a go. Every thread will be woken up. They will all wake up in turn. They will all get a chance to hold the lock. They will all receive the signal, get the lock, do the thing that they need to do in that critical section, and then release the lock. And all of them are going to get this because we did the broadcast instead of the signal here. In this case, all of them finish after releasing that, so our main thread is going to finish because join is going to return for all the threads that we've got here. Yeah?
The first couple lines of output is a little bit jumbled, contact switching between the two threads.
So the received signal in thread, received signal in thread. This is a problem that we have with printf is buffering output, and the threads of execution are kind of getting their turns to go in what appears to be a random order. This is ultimately coming down to scheduling, and it's really more that printf is buffering. If I change this to use write instead of printf, then it should print in probably the same order. I'd expect it to print in the same order that I expect it to print in the order that I would expect it to print in. I'd expect it to print in the correct order for what we're envisioning to be happening here, yes. But printf is buffering, so it's kind of holding stuff here. Yeah. Okay, so like I said, this is kind of a mechanical use of condition variables. What we're going to do tomorrow's class is we're going to spend some time writing some realistic code that uses condition variables. So at this point, you should be able to use condition variables in a program in a basic sense, but I do want to spend some time working through this realistic example. And in tomorrow's class, what we'll also try to do is spend some time taking a look at assignment 3. That's it for today. I hope you all have a great rest of your